So, what should we do about all of this? Well, Salzberg is going to tell us now in section 3.5 called the recommended approach. In the previous section, he wrapped up his discussion of a number of things that pose methodological problems in a lot of experimental design in machine learning, particularly around classification. And what he talked about at the end was overgeneralizing from your results. Certainly, when we're taught to write, we're taught to take a stand in our papers and the conclusions, right? And certainly a stand in classification, talking about methods, often involves saying, my method is going to work for everything, or it tells me better paper would be my method tells me something about the broader world. In fact, you should always be careful about how far out you do try to generalize. And the basic deal is in machine learning, the population you trained and tested on is about as far as you should probably go. So one time I would do hedging is about generalization. I hate when people use the term weasel word for the things people do to avoid making strong claims about generalizing, because it ain't weaseling, it's just being scientifically honest. Okay, so with that, what does Salzberg tell us to do? I recommend that you look at the paper and read along as we do this, because it's hard to follow this kind of level of technical detail without it. Okay, 3.5, a recommended approach. Although it is probably impossible to describe a methodology that will serve as a recipe for all comparisons of computational methods, here is an approach that will allow the designer of a new algorithm to establish the new algorithm's comparative merits. I would throw in here, Kevin speaking now, also to establish the new algorithm's weak points too, which in a lot of ways is more interesting than the merits. Okay. So step one, choose other algorithms to include in the comparison. Make sure to include the algorithm that is most similar to the new algorithm. I'm going to interject here my restatement of this, which would be choose baselines that are not trivial. There is an excellent chapter by Phil Resnick and Jimmy Lin, oriented towards evaluation in natural language processing, that has really nice coverage of the different kinds of baselines that you might use. Okay, so we're going to choose other algorithms. Make sure to include the algorithm that's most similar to the new algorithm is a really good one, because the fact is, you're often in our field, the new one is not that different from the old one. And if you're going to claim a big difference in performance, well, it better be a big difference, right? Number two, choose a benchmark data set that illustrates the strengths of the new algorithm. For example, if the algorithm is supposed to handle large attribute spaces, choose a data set with a large number of attributes. Now, I want to interject in here. I want to refine this a tiny bit. So I would, where Salzberg says, choose a benchmark data set that illustrates the strengths of the new algorithm, I would say choose a benchmark data set that is appropriate for testing whatever you think the advantages of this algorithm are. For example, if it's supposed to handle large attribute spaces, choose a data set with a large number of attributes. Just a little bit different way of putting that. Point number two I would like to make here is that when you are writing your paper, it's really, really useful to say in the material section, why did you choose this particular data set? What makes it good for testing your hypothesis, answering your question, evaluating your classification performance, whatever it is you're trying to do. Back to the paper. 3, divide the data set into K subsets for cross-validation. Okay, so the idea here is there's an assumption here, which is that we're going to be doing cross-validation, right? A typical experiment uses k equal to 10, though other values may be chosen depending on the data set size. For a small data set, it may be better to choose larger k since this leaves more examples in the training set. 4, run a cross-validation as follows. And here it becomes impossible to follow, I think, or difficult to follow if you are not looking at this paper. Okay. Number 4, run a cross-validation as follows. 5 parts to this. A, for each of the k subsets of the data set D, create a training set T equals the D minus k. So I think he's saying you're going to do this in every step of the cross-validation. Okay, B, divide each training set into 2 smaller subsets, T1 and T2. T1 will be used for training and T2 for tuning. The purpose of T2 is to allow the experimenter to adjust all the parameters of his algorithm. This methodology also forces the experimenter to be more explicit about what those parameters are. And I do love the idea of being explicit about what those parameters are. Typical machine learning packages might have 30 different parameters, and if you don't specify what they are, not only does the reader of your paper not know, you might not know either. So let me think through what he's saying to do here. So I think when he says T1 will be used for training and T2 for tuning, the basic idea there is you'll build your set of features and based on that train a classifier on dataset T1 and then use T2 to explore the parameter space for the classifier itself, I think. Okay, C, once the parameters are optimized, rerun training on the larger set T. Now, I'm not sure that's what he means here because, oh, yes, it is. Yes. So T is the data set itself minus k, whatever the subset of the data set is. Finally, measure accuracy on k, that's our held out data, and then overall accuracy, of course, I hate the word accuracy, let's say overall performance is averaged across all k partitions. And these k values also give an estimate of the variance of the algorithms. And I'm going to throw in here, tell your reader what the variability is. So Salzberg mentions variance specifically, it might be standard deviation actually, if you have a normally distributed set of results, maybe the interquartile range, but do tell the reader something about what the variability is across those k-folds. Personally, I'd rather have a classifier that's not very variable than have one with a higher mean performance, but that is in fact pretty variable across folds. That's not a good thing because you don't know where in that range that classifier is going to perform when you're depending on it. All right, so finally, step 5, to compare algorithms, use one of the tests that he suggests earlier in the paper. If you're doing natural language processing, what those tests are might differ. And I don't know if Salzberg himself would suggest the exact same statistical tests, but let me say, do be careful about what tests you use. It's probably not going to be the t-test, right? Now, back to Salzberg. It may be tempting because it is easy to do with powerful computers to run many cross-validations on the same data set and report each cross-validation as a single trial. Oh, yeah, that would be tempting. So that's a mistake I could make. In that case, yeah, what I would be thinking would be something like this. My partitions were were random every time, they were different every time, let's say I used a different seed every time, so didn't I do different experiments every time? Well, that would be a mistake, and Salzberg is going to explain why. It may be tempting, because it is easy to do with powerful computers, to run many cross-validations on the same data set and report each cross-validation as a single trial. However, this would not produce valid statistics because the trials in such a design are highly independent. Interjection here, remember that most common statistical hypothesis tests make an independence assumption that is widely violated in classification data sets, and probably even violated even much more in natural language processing data sets, because there's a general lack of independence in human language. So back to Salzberg, the above procedure applies to a single data set. If an experimenter wishes to compare multiple data sets, then the significance levels used should be increased. Actually, I think he means decreased, in that, when you start out with any given significance level, you're going to divide it by a number that's higher than 1, so that is going to go down. Then if an experimenter wishes to compare multiple data sets, and the significance level should be increased or decreased using the Bonferroni adjustment. And remember, I told you earlier about a paper by Rotem Dror and her colleagues that talks about exactly this. Statistical tests across multiple data sets in natural language processing. Back to Salzberg. This is a conservative adjustment that will tend to miss significance in some cases, but it enforces a high standard for reporting that one algorithm is better than another. And that's true. It is a high standard because you certainly with Bonferroni, at least in bioinformatics, can end up with a p-value you have to hit for significance that's so low you may never hit it. There are alternatives to this, so false discovery rate. I don't think it was being used much when this paper was published in '97. It's a big thing now in some communities, particularly around bioinformatics, computational biology, stuff like that. Okay, so that finishes up that section of the paper, and we'll come back for the conclusion.